Good morning, students. So hope all are fine. So today we will start the session now. So hope my screen is visible to all, right? Okay. So today
Yes,
we
sir.
are
It is
going to
visible, sir.
discuss about. Hello, sir. Ram, sir.
Yes, sir. It is visible, sir. You can continue.
Okay, sir. So today we are going to discuss about the content for CA2 test. Okay, so we are going to revise the topics which are available for CA2. So this is the portion for CA2. So take this slide snapshot. So these are the portions for CA2 exam. Take a snapshot. So these are the things we are going to revise in this session. So these things are already discussed. Anyway, for exam purpose, we are going to just revise these content. Okay, so we will start with K-map. So already we have discussed K-map, Karnaugh map. So this Karnaugh map is used for minimizing the Boolean function. Okay, so while minimizing the Boolean function, we will follow some rules. Okay, so here we are going to discuss the rules followed for K-map minimization. Okay, so the number of min terms in a group must be a power of 2. So while grouping the number of ones, or you can say min terms, okay, the number of min terms or number of ones should be followed power of 2. Okay, it should be power of 2. That means 2 power 0, 2 power 1, 2 power 2, 2 power 3, like that. Okay, so you can group one number of min term or two number of min terms or 4 or 8 or 16, 64, like that. Okay, so the number of min terms in a group should be a power of 2, right? So this is the example for grouping the number of min terms. So here in this group, we are having two min terms. Okay, two number of ones are grouped in this group. Here we are having four number of ones or four number of min terms. Okay, then a group should contain at least one number of min term or one number of one. Okay, but these two ones are not combined each other. Okay, we cannot make these two ones in a single group. Okay, that is not allowed, because while grouping the number of min terms, you can group the number of ones in vertical manner or horizontal manner. Okay, we cannot group the number of ones in diagonal, right? So here in this example, 2-bit K-map, we are having two ones that are available in corners. So we have to group as separate groups. Okay, each one should be grouped separately, right? Then each grouping should be as large as possible to get maximum simplification. Okay, so to get a better simplified Boolean expression, okay, we should always try to combine maximum number of min terms in a K-map. Then only you will get simplified Boolean expression. So in this example, there are four number of ones. So you can combine four number of ones like that, like a single group. Okay, so this is the maximum possible group with four min terms. Okay, actually this came up having eight min terms, but here four min terms are highlighted. Okay, so here the maximum possible number of ones to group is 4, right? So while grouping the number of ones or min terms, we should always try to follow maximum number of ones to get a simplified Boolean expression. Okay, so if you are getting much simplified Boolean expression, then while drawing the Boolean circuit, okay, if you are realizing the Boolean digital circuit, that will result in minimized number of gates. Okay, that required lower number of gates. So while grouping the number of ones, we may overlap the minterms. Okay, so groups may overlap. Okay, so here the adjacent cells having number of ones that are grouped as 2. Here, this corner one is common for both the group. Okay, so this one is overlapped. So like this, you can overlap the number of ones, right? So overlapping in a K-map is allowed while grouping the number of ones. So grouping may be horizontal and vertical, but not diagonal. So as I already told, while grouping the number of ones, you can either group as horizontal ones or vertical ones, but not diagonal. Okay, so diagonal grouping is illegal in K-map. A cell may be grouped more than once. Okay, a single cell can be grouped more than once. Okay, the only condition is that every group must have at least one cell that does not belong to any other group. Okay, so if you are grouping number of ones, okay, as a single group, for example, group A, that group A should have at least one minterm. That one minterm does not belong to other grouping, right? So here in this example, this one is common for both the group, but this is only belongs to this group. This one is belongs to only this group. Okay, so this cell is in two groups. This particular cell is common for two groups. These two cells are different group. Okay, this one is belongs to this group. This one is belongs to this group only. Okay, but this one is common for both the groups. Okay, so groups may be folded around the map, right? So leftmost cells here can be grouped with rightmost cells. Okay, so here we are having one example. The first cell having 1, 1. Similarly, at the rightmost cell, fourth cell having one more 1. So you can combine these two ones. Okay, this one forms one group. Like that, you can take leftmost and rightmost cells to group as a single group, or maybe two more groups. Okay, the leftmost cell in a row may be grouped with the rightmost cells. This is the example. So leftmost cell can be grouped with rightmost cell. Similarly, the top, okay, top and bottom. Okay, so top and bottom rows can be grouped as single cell. So here we are having two number of ones in top row. Here also we are having 2 ones in the bottom row. Okay, these 2 and these 2 ones can be grouped as single group. Okay, that means 4 1 groups. Then one cell grouping. So this is the example for one cell grouping. So this is a 2-bit K-map. This is your 3-bit K-map. So here we are having a number of ones that all the number can be grouped as a single group. Okay, we cannot combine these numbers because that will result in diagonal grouping. So diagonal grouping is not allowed in the K-map. So you can group these ones as a separate groups. Okay, so 2 cells grouping. So you can do 2 cell grouping like this. So this type of grouping should have 2 number of ones in a group. Okay, so like this. So these are the example for 2 cell groupings. Then 3 cell groupings not allowed in the K-map because we should follow power of 2, right? So after 2 cell grouping, we should go for 4 cells, right? So this is the example for 4 cell grouping. Okay, so here horizontally we can combine 4 number of ones, or at the corners we can combine 4 number of ones, or top and bottom, or left and right. Okay, anyway, a group should have 4 number of ones. Then 8 cell grouping. Okay, in this 8 cell grouping, we should combine 8 number of minterms or 8 number of cells as a single group. So these are the some example for 8 cell grouping. Okay. So illegal grouping. So what are the conditions we can say that these type of groupings are not allowed in the K-map or illegal grouping? Okay. So if number of ones are available in diagonal manner, okay, so you cannot combine these diagonal number of ones as a single group because diagonal grouping is not allowed in the K-map. Okay, so this is an illegal grouping. And also, we cannot combine vertical and horizontal ones. Okay, so this is also not allowed. Okay, anyway, this group having 4 number of ones, it follows power of 2 rule. But the combination or the position of number of ones is not in horizontal or vertical manner. Okay, it combines both. Okay, so this type of grouping is also not allowed in the K-map. Then number of minterms should follow power of 2. So as already discussed. So here in this example, we are having 3 ones in a single group. So this kind of grouping is not allowed. Okay, so this group is illegal. Okay, and however, this one is valid one because this group contains 2 ones only. Okay, it follows power of 2 rule, right? Then redundant grouping. Okay, so it is a group whose all minterms are overlapped by the other groups, right? So you can remove or ignore this kind of grouping, right? So what is my redundant group? So in this example, we are having 4 number of ones. That 4 number of ones can be grouped into 2. Okay, so this is where group 1, this is where group 2. Okay, so from these 2 groups, 4 ones are covered. Then additionally, there is a third group. This group is not needed. Okay, so you can ignore this kind of grouping because this group has a number of ones. That number of ones are already available in other groups. So these kind of groups may be avoided. Okay, this kind of groups is called as redundant group. Okay, so you can ignore or remove that kind of grouping. Okay, so if you are removing the redundant group like this, then you will get very simplified Boolean expression. Okay, so this is the another example. Here we are having 4 groups, 4 2 cell grouping, 1, 2, 3, 4. Okay, so these 4 cells combine all the ones. Okay, it covers all the ones available in this K-map. Additionally, there is a 5th group. Okay, this 5th group contains number of ones that are all available in groups from 1 to 4. So you can ignore this 5th grouping. Okay, this 5th group is nothing but redundant group. You can ignore that 5th group. Okay, so we'll see some problems based on K-map. So we know the procedure to simplify the given Boolean expression using K-map. Okay, so this is the given Boolean expression in terms of minterms, sum of minterms. So f of x comma y, which is equal to sum of minterms 0 and 3. Okay, so it is a 2-bit K-map. So we should have K-map like this. Okay, so K-map should have 4 cells. Okay, so x is denoted in the rows and y is denoted in the columns, right? So here the minterm 0 and 3 is given in the Boolean function. So you can number the cells and mark the 1 in corresponding cells. Okay, so here there are 2 ones, but the position is like diagonal. So you can group these ones separately. We cannot combine these these two ones as a single group. That is not allowed in the K-map. So you can combine individual group. Okay. After grouping the number of ones, then you can get the minterm. Okay. So this one having primed x parameter, x value and primed y value. That is x bar, y bar. Right? So this will give x bar, y bar, or x dash, y dash. This is one minterm. The another minterm is from second one. Okay, so here this one belongs to cell number 3, that will give a minterm x and with y. Okay, xy. Right? So here is the Boolean expression. By summing these two minterms, you will get the final Boolean expression for the given function. So that is equal to x prime and with y prime, or with x and y. Okay, x dash, y dash plus xy. Okay, that is the x nor function, right? X nor with y. Okay, you can also simplify like this. Then this is the another example. Here also we are having two variables. So for cell map, zeros and ones. So here we are having minterm 0, 1 and 3. Okay, so I'm putting the number of ones in corresponding cell and I'm trying to group the number of ones. Okay, so here you can group number of ones into two separate groups. Okay, this is one group, this is the another group. Okay, from this first group you will get x prime. From the second group you can get the value y. Okay, by combining these two minterms, this is the final Boolean simplified expression, x prime plus y. Okay, so this is the third example. Here also we are having two variables. So 4 cells, 0, 1, 2, 3. Okay, here the given minterms are 0, 1, 2 and 3. Okay, so when you are putting the number of ones in corresponding cells, then all the cells are having number of ones. So you can combine maximum number of ones in the K-map. Okay, so here you can combine all the ones. Okay, 4 ones can be grouped as a single group. Okay, so that will give a very simplified Boolean expression. Okay, that is equal to 1. Right? So for all the combinations of these x and y inputs, the result will be 1. Right? So this is the another example. F of x comma y comma z is equal to x prime y z plus x prime y z prime plus x y prime z prime plus x y prime z. Okay, so this Boolean expression can be represented as sum of minterms like this. Okay, so this is a 3 variable Boolean expression. So we need to draw 3 variable K-map like this. Okay, so I'm numbering the cells and I'm putting the 1 in corresponding cell. Okay, so here we are having minterms 2, 3, 4, 5. Okay, I'm putting the number of ones in respective cells 2, 3, 4, 5. Okay, after putting the number of ones, and I'm trying to group the number of ones. Okay, here also 2 possible groups. From these 2 possible groups, we can get minterm like this. From group 1, you can get x prime y as a minterm. From the second group, you will get x y prime. Okay, by summing these 2 minterms, then you will get x or of y. Right? So x prime y plus x y prime. This will give x XOR with y. Right? Another example is f of x comma y comma z, which is equal to sum of 0, 2, 4, 5, 6. Okay, so this is also 3 variable Boolean expression. So we need to draw 3 variable K-map, that is 8 cell K-map. So this is the 8 cell K-map, and I am putting the number of ones in respective cells. Okay, 0, 2, 4, 5, 6. Okay, then I'm grouping the number of ones. Here you can combine leftmost and rightmost cells. Okay, so maximum possible number of ones is 4. Okay, by taking leftmost cell and rightmost cell, you can combine 4 number of ones, right? So this is my first group, then this is my second group, right? So from the first group, I will get minterm like this, Z prime. Okay, from second group, I will get minterm X, Y prime. By summing these two minterms, then Boolean function will be X prime plus X, Y prime, right? So this is the another example. Here also we are having 3 variables. So 3 variable K-map, right? So the minterms are 0, 1, 2, 3, and 7. Okay, I'm putting the number of ones 0, 1, 2, 3, 7. Okay, so in this group, you can combine 4 number of ones as maximum, right? So maximum possible ones are 4. Okay, so this is the first group. This is the second group, right? So from these two groups, you will get X prime and Y Z as a mean terms. By summing these two, this is the final Boolean expression. Okay, X prime plus Y Z, right? So this is the another example. So in this example, we are having 4 variables, f of w, x, y, and z, which is equal to sum of minterms 0, 1, 3, 8, 9, 10, 11, 12, 13 up to 15. Okay, so it is a 4 variable Boolean expression. So we need to draw 4 variable K-map with 16 cells, right? So this is the position for variables, and the number of cells are like this. Okay, 0 to 15, right? Then I'm putting the number of ones in respective cells: 0, 1, 3, 8, 9, 10, 11, 12, 13, 14, 15. Okay, after putting the number of ones, next we have to group the number of ones, right? So here, the maximum number of ones possible is 8. Okay, so you can combine these 8 ones as a single group. Okay, so this is the group 1, this is group 2. Okay, so next you can have 4 number of ones. Okay, so this is my next group. Okay, top row and bottom row. Okay, by combining these two rows, top and bottom rows, you can have 4 number of ones. Okay, because we are trying to group always maximum number of ones. Okay, you can also group cell 0 and cell 1, but that will give only 2 number of ones. Okay, but it is also possible to group cells 0, 1, 8, and 9. Okay, that will give 4 number of ones group. Okay, 4 cell group. Okay, so compared to 2 cell group, 4 cell group give minimized minterm. Okay, that's why we are going for 4 cell grouping, right? So this is my second group. This is my third group. Okay, so here also we are trying to combine maximum number of ones. Okay, so here in this example, you can observe that there are more number of ones are overlapped, right? So from the second group, okay, in this group, these 2 ones are overlapped. These 2 ones are already grouped in group 1, but while doing second group, these 2 ones are overlapped, right? So while doing grouping in third time, okay, this third group having 3 ones that are all overlapped with other 2 groups. Okay, so this one is also available with group 2, right? This is overlapped one, and here this one is available for group 1 as well as group 2, right? So this one is available with group 1, right? So these 3 ones are overlapped. Anyway, this third group is valid one because this group having this single one which is not available in other groups. Okay, so because of this reason, this third group is valid one. Okay, so from these 3 groups, you will get 3 minterms. Okay, so x bar z, that is from third group, x prime, y prime, that is from second group, W, which is from first group. Right? So from this example, you can also observe that the maximum number of ones gives minimized minterm. Okay, this minterm contains only one variable. Okay, but the 4 number of ones results in minterm which contains 2 variables. Okay, so like that you can observe the difference. Okay, why we are going for maximum number of ones for grouping, right? So this is the final Boolean expression. So W plus X prime Y prime plus X prime Z. Okay, it can be simplified further like this. Okay, W plus X prime and with Y prime plus Z, right? So so hope all are understand the K-map minimization, right? So 2-bit, 3-bit, 4-bit. Okay, so 2 variable Boolean expression, 3 variable Boolean expression, 4 variable Boolean expression. Okay, so இதில் நம்ம K-map draw பண்றது, numbering ஒவ்வொரு செல்லையும் எப்படி number பண்றது, then based on the given minterm, how to put the number of ones in the K-map, and how to group the number of ones, then how to get the minterm from that each group. Okay, so after getting minterm from each group, then you can sum all the minterms like this. Okay, so if it is possible, you can further simplify, otherwise you can take it as a final simplified expression. Okay, so next we will go for K-map with don't care condition. Okay, so a don't care term is a combination of variables whose logical value is not specified. Okay, it may be 0 or 1. Okay, in a function, the don't care term may have either 0 or 1. Okay, that is not specifically mentioned, right? So such a term can be marked with an X or small d. Okay, in a K-map, right? So don't care alone not mapped and simplified. Okay, so in K-map, don't care alone cannot be mapped. Okay, if it is a case, you can ignore that grouping, right? So when you are grouping in the K-map with don't care, a single group should have a logic 1. Okay, so at least one minterm should be in the group. Okay, don't care alone cannot be form a group. Okay, so here is the example. So in this example, the left side K-map shows 2 grouping. So this is one group, 2-cell group. So this 2-cell group is allowed. Okay, so this group contains one don't care variable, one valid minterm. Okay, but if you are going for this second group, okay, this group contains only don't care terms. Okay, so these don't care terms cannot be allowed in the K-map. So this is not allowed in the K-map. So this is a valid group. Okay, this is allowed in the K-map. Okay, so this can be done like this. Okay, so from this K-map, you can get only one group, right? So this group contains one minterm and also don't care. Okay, you can mix the don't care variables and minterm, but don't care alone you cannot group in the K-map. That is not allowed in the K-map, right? So this is the illegal grouping. This is a legal grouping, right? So it need not be used in grouping if does not cover a large number of ones. What is that meaning? Okay, so here is the example. So here we are having 4 number of ones and 2 number of don't care variables. Okay, so here by grouping these 4 ones like this, it covers all the ones available in the K-map. Okay, this group alone we have covered maximum number of ones, okay, that are available in the K-map. Okay, the second group, this group also contains don't care variable and the minterm, but the second group covered number of ones are already covered with group 1. So in this case, this second group is not allowed. That is not needed. You ignore this second group. So you can take only the first group. Okay? Because this first group alone we have covered maximum number of ones. Right? So this is an illegal mapping. This is a legal mapping. Okay? So here is the example. So here we are having a function f of x, y, z, which is equal to summation of 0, 1, 3, 7. And the don't care terms, d of x, y, z, which is equal to summation of 2, 5. Okay. So you can draw the 3 variable CAMAP with 8 cells. Okay. So this is the 8 cell CAMAP. So here I'm going to put the number of ones, that is number of min terms in this cell, okay, by representing as 1. Okay, so here we are having 4 min terms, 0, 1, 3, 7. So 0, 1, 3, 7. Okay, we have placed the min terms in the CAMAP. And also we need to place don't care condition also. Okay, so 2 and 5, these are don't cares. Okay, 2, 5. Right? Then here, so what can be done? Okay, how to group the number of ones? And also keep in mind that while grouping the number of cells, we have to try to always maximum number of ones. Right? So here you can group like this. Okay, this group contains 4 cells. Right? Maximum number of cells from this group. Okay, the another group is like this. Right? So here also we are trying to group maximum number of ones. Okay, 4 number of cells. Right? So from first group you will get min term like this. From second group you will get a min term like this. Okay, so this is the final simplified expression, x bar plus z. Okay, that is the function f of x comma y comma z. Another example with the 4 variables. So this is the 4 variable CAMAP, okay, with the 16 cells named from 0 to 15. Okay, so here we are having min terms 5, 6, 7, 12, 30. Okay, I am putting the number of ones in respective cell 5, 6, 7, 12, 30. Okay, and then we have some don't care variables. Okay, 4, 9, 14, 15. Okay, 4, 9, 14, 15. Okay. Actually, this 14 is don't care. It should be don't care. It should be represented x. Okay. Okay. Now, so how to group this CAMAP? Okay. So you can try to group 8 number of cells. Okay, from 4 to 15. Right. So you can do group like this. Here you can ignore this 9th cell because it is a don't care. Okay, if you try to group that 9th cell, it will result in 2 cell. Okay, so that should be redundant one. So you can avoid that grouping. Okay, so only we have one group in this CAMAP. Okay, from this CAMAP you will get a min term x. Right? So hope after grouping the number of ones, you know the procedure to get the min term, right? So we have to take the common term from the left side or from the top side. Okay, so here 8 cells are grouped in a single group. Okay, so if you are seeing the top, okay, so here we are having 2 variables that are all changed. Okay, so there is no common term in this top portion, but in the left portion we have common term, that is x. Okay, so this common term can be taken as a min term, right? So this is the final simplified Boolean expression for this given Boolean function. Okay, so f of w, x, y, z, which give x. Then we will go for binary codes. Okay, any doubt in this K-map minimization? If you have any doubt, you can ask now. Otherwise, we will move on to binary codes. See, we all discussed this content. That's why I'm moving fast. That's why I'm not spending much time on that. Okay, so hope all can recall the things. Okay, this is not new for us. Okay, just this session is meant for recalling the things. Okay, which is already discussed in the previous sessions. Okay, shall we move further? Okay, so next one is binary codes. Okay, so by codes. Okay, what is meant by code? Okay, so a code means a group of symbols which is used for predefining something. Okay, to represent a predefined rule. Okay, a group of symbols with predefined rule is called as code. Okay, a binary code is a group of bits representing any discrete element of information. Right? So binary codes are used for representing numbers, alphabets, and special characters, etc. Right? So classification of binary codes. So we have 4 different binary codes: weighted code, non-weighted code, alphanumeric codes, error detection, and correction codes. Okay, so example for weighted code is BCD. Example for non-weighted code is gray code, XS3 code. Alphanumeric codes, ASIC, Unicode. Okay. Error detection and correction codes are parity code, Hamming code, right? So we will move on to BCD, binary coded decimal, or you can say 8421 code, right? So in this representation, we are having 16 possible combinations from 0000 to 111. That is 0 to 15. Okay, because we are having 4-bit numbers. The 4-bit number results in 16 combinations. Okay, from 0 to 15. Okay, from 0 to 15. Okay, among them, we are only use 10 combinations. Okay, 6 combinations are ignored. Okay, in binary decimal code, binary coded decimal, we will use only 10 possible combinations. We will ignore, or we will not consider other 16 possible combinations. Okay, so what are they? From 10 to 15. Okay, 1010 to 1111. These combinations are don't care terms. Okay, which is not valid in this BCD. Okay, we are not using this combination in BCD, right? So generally, the BCD codes are denoted with a subscript BCD. Okay, so like a binary value, octal value, hexadecimal value, like that. Okay, if you are representing hexadecimal value, you will write a value in bracket, then followed by 16 as a subscript. Okay, so it is also called as packed BCD, right? So these are the example for binary coded decimal. Okay, so this is the decimal numbers 0 to 15, then corresponding binary values, then corresponding BCD values. Okay, so here you can observe that the decimal value 0 to 9, okay, decimal value 0 to 9 are represented like this. Okay, 0002 to 1001. Okay, these 10 combinations are valid in this BCD. Okay, that is similar to binary. But if you are going for above that value, okay, that means 10 to 15. Okay, we will not follow the rule followed in the binary system. Okay, we will follow a separate rule in the BCD, right? So here after 1001, then again we will start from 0. Okay, then we are having 0001. Okay, that means you can split this 2-bit decimal value into 2. Okay, then you can give corresponding BCD value for each digit. Okay, 0. This 0 can be represented as 0000 in BCD system. Okay, this 1 can be represented as 0001. Okay, so by combining these two terms, then you can have 10 in binary coded decimal, that is BCD. Okay, so the decimal value 10 can be represented as 0001 0000. Okay, so this is the BCD representation for the decimal value 10. Similarly, 11, 12, 13, 14, 15. Okay, so here you can have 15, so you can split into 2. Then you can represent each decimal digit in terms of 4 bits. Okay, so this 1 can be 0001, 5 can be 0101. Okay, so this is the BCD value for decimal value 15. Okay, so these are the example for BCD. So representing the decimal number 34 in BCD. Okay, each digit is represented in 4-bit code. Okay, we will consider each digit in decimal. Okay, we will take each digit separately and represent as 4-bit code. Okay, so here we are having 34, the decimal number. So 3 and 4 considers each bit. Okay, so 3 can be represented like this 0011, 4 can be represented like this 0100. Okay, by combining these two, then you will get a BCD value for decimal number 34. Okay, so 34, which is equal to 0011 0100. Okay, in subscript we should denote BCD. Okay, the another example, the decimal number 100. Okay, so here also we have to split this number into 3. Okay, so each digit can be represented by 4 bits. So 1 can be represented as 0001. 0 zeros are represented as 4 zeros. Okay, then another example, decimal number 974. Okay, so here also we are splitting the digit and each digit is represented by 4-bit code. Okay, so 9 is 1001, 7 can be represented as 0111, 4 can be 0100. Okay, then another example, 8201. This is the example for 8201. So 8, 1000, 2 can be represented as 0010, 0 can be represented as 4 zeros, 1 can be represented as 0001. Okay, then with this basics we will move on to BCD addition. Okay, so addition means we are trying to add 2 input data. Okay, so here add the 2 BCD numbers using the rule for binary addition. Okay, so here we are going to perform BCD addition. For that also we are going to follow BCD addition rule. Okay, so we all remember the binary addition. Okay, so based on that binary addition only we are going to add 2 BCD numbers. Okay, if the 4-bit BCD sum is less than or equal to 9, it is a valid BCD number. Otherwise it is a non-valid or invalid BCD number. Okay, then you have to correct the invalid BCD into valid BCD by adding 6. Okay, so these are the basic rules we have to follow while performing BCD addition, right? So if you are adding 2 BCD numbers, okay, the sum of BCD should be less than or equal to 9. Okay, then only the result is valid one. Okay, if that result is greater than 9, then it is a invalid BCD number. So we have to correct that invalid BCD number into valid BCD number by adding 6. Okay, so this is the example. So here we are having 2 decimal numbers 5 and 4. Okay, so in decimal manner, if you are adding these 2 decimal numbers, you can get result as 9. Okay. In BCD system, 5 can be represented as 0, 1, 0, 1. 4 can be represented as 0, 1, 0, 0. Okay. Then after representing each decimal value in BCD, then we have to follow binary addition. Okay. Binary addition means from LSB to MSB, we will add bitwise. Okay. 1 added with 0, that will give 1. 0 added with 0, result in 0. 1 added with 1 gives sum 0, carry 1. That carry will be taken over here. Okay. Then 1 plus 0 plus 1, result in 1. Okay. So this is the result. Okay. By adding 0, 1, 0, 1 with 0, 1, 0, 0, you will get result 1, 0, 0, 1. Okay. This is a valid BCD because it is equal to 9. Okay. The result is equal to 9. Then it is a valid BCD. Right. So this is the another example. Here we are having two decimal numbers 5 and 6. We are going to add 5 and 6. So you will get 11 as a result. Right. So 5 can be represented as 0, 1, 0, 1 in BCD. 6 can be 0, 1, 1, 0. By adding these two numbers, then result will be 1, 0, 1, 1. Right. So 1, 0, 1, 1. Right. It is 11 in binary, but this is not a valid BCD sum because it is greater than 9. So to correct this invalid BCD, to get a valid BCD, we need to add 6. Okay. 0, 1, 1, 0. Okay. So by adding these two values, then you will get valid BCD result. Okay. 1, 0 will give 1. 1 plus 1, 0, carry 1. 1 plus 0 plus 1, sum 0, carry 1. Okay, again 1 plus 1 plus 0, sum 0, carry 1. Okay, here there is a carry. Okay, that carry is considered separately. Okay, so here we got 4-bit result. Okay, so this is one BCD number, this is another BCD number. Okay, so to get a 4-bit representation with the carry, you can append number of zeros. Okay, in the left side. That means towards the MSB. Okay, so this 4-bit represents decimal value 1. This 4-bit represents decimal value 1. So the result is 11. Okay, as got in the conventional adding method. Okay, decimal addition உங்களுக்கு 11 கிடைச்சிருக்கு அதே மாதிரி BCD additionலயும் உங்களுக்கு 11 கிடைச்சிருக்கு. Okay, so like that you can perform the BCD addition. So this is the another example. Here we are taking 29 and 28. Okay, if you are adding these two numbers, the result is 57. Okay, so here we are going to represent 29. Okay, in BCD, so 2 can be represented as 4-bit, 0, 0, 1, 0. 9 can be 1, 0, 0, 1. Right? Then 2, 9, 0, 0, 1, 0. 8 is 1, 0, 0. Okay, so here we are going to add these two numbers. So binary addition, we are going to follow binary addition. 1 plus 0, 1, 0, 0 gives 0, 0 plus 0 gives 0, 1 plus 1 gives sum 0, carry 1. Okay, this lower nibble generates carry bit to the higher nibble. Okay, so this higher nibble should be added, this carry bit is added with higher nibble. So 1 plus 0 plus 0 gives 1, 1 plus 1 sum 0, carry 1. So 1 plus 0 plus 0 will give 1, 0 plus 0, 0. Okay, so this is the result. Okay, so if you are seeing the result, this 4-bit represent 5 less than 9. This 4-bit represent 1 less than 9. Okay, but this is not a valid BCD. Why? Because here this lower nipple generates a carry bit to the higher nipple. So this lower nipple is a invalid BCD. Okay, so to get a valid BCD, we need to add 6 with lower nipple. Okay, with this lower nipple alone, we have to add 6 because this is only invalid BCD representation because it generates a carry bit. Okay, carry from lower nibble. If lower nibble or higher nibble generates carry, okay, then that particular nibble, okay, it may be lower nibble or higher nibble, okay, that should be invalid. Okay, so to get a valid BCD, we should add with 6. Okay, so here this lower nibble generates carry bit, so it is a invalid BCD representation or BCD number. So to get a valid BCD number, we should add 6. So 0, 1, 1, 0 should be added with this lower nibble 0, 1. Okay, so the result is 1 plus 0, 1, 0 plus 1, 1, 0 plus 1, 1, 0 plus 0, 0. Then here there is no number. So here this number will repeated here, right? So as a result, we are getting 0, 1, 0, 1. It represents 5. 0, 1, 1 represents 7, right? So 57 has got in the decimal addition, right? Hope it is clear to all of you. So this is the next example. So 99 plus 76. Okay, we are going to add numbers 99 and 76. Okay. So this is the result 175, 175. Okay, so 9 can be represented as 1001, 1001. So 99 can be represented as like this. Okay, in 8-bit representation. Okay, 76 can be represented like this, 0, 111, 0, 110. Okay, then we can add binary bits. 1, 0 gives 1, 0 plus 1, 1, 0 plus 1, 1, 1 plus 0, 1. Okay, similarly here, 1 plus 1, sum 0, carry 1. So carry 1 plus 0 plus 1. Sum 0, again carry 1. Carry 1 plus 0 plus 1. Sum 0, carry 1. Carry 1 plus 1 plus 0 gives sum 0, again the carry 1. Okay, so this higher nibble generates carry. So obviously it should be invalid BCD number. Okay, so to correct that invalid BCD number, we should add with 0, 1, 1, 0, that is 6. Okay, but here also lower nibble. Okay, if you are seeing the lower nibble, here we are having the number which is greater than 9. Okay, it represents 15. So this is also invalid BCD number. Okay, both lower nibble, higher nibble are invalid numbers. So we should add 6 with both lower nibble and higher nibble, right? So as a result, you will get the valid BCD number. Okay, so from this lower nibble addition, you will get 0, 1, 0, 1. Higher nibble addition, you will get 0, 1, 1. We should carry this 1 to the result. Okay, so 1, 0, 1, 1, 0, 1, 0, 1. Okay, so to represent in 4-bit, you can append number of zeros in the left side. Okay, so this is one number, okay, which represent decimal value 1. This represents 7. This represents 5. Okay, that is 175. Okay, valid BCD number. Right, so here is the hint why we are adding value 6 with both the higher and lower nibbles. Okay, lower nibble is greater than 9, higher nibble generates carry bit. That's why we are adding 6 with both the values. So this is the another example, 9276. So this can be represented like this: 1001 0010 76 0 111 0 110. Okay, so here you can add these lower nibbles. By adding these two lower nibbles, you will get 1000, and also you will get result by adding these higher nibbles, that is 4 zeros, and also this addition generates carry bit. Okay, so due to this carry generation, this higher nibble is invalid. So we are adding 6 with higher nibble only. Okay, because lower nibble value is 1000. It is a valid BCD number. Okay, higher nibble also having 4 zeros. It is also less than 9, but this higher nibble generates carry 1. So it is a invalid BCD number. So to get a valid BCD, we are adding 6, right? So by doing addition operation, then you will get result like this. Okay, this will be carried over here. Then here you have to add these two numbers. So 0, 1, 1, 0. This is the result. Then this one is carried over here. Okay, so to get a 4-bit representation, you can add append number of zeros. Okay, so this gives 1, this gives 6, this gives 8, 168. That is the result. Okay. So hope all are understand the BCD addition, right? Then we will see the gray code. So what is meant by gray code? Okay, so it is a non-weighted code. Okay, non-weighted code means there is no specific weight assigned to each bit position. Okay, we are not giving any weightage to each bit. Okay, like binary. Okay, we will not give any weightage to each bit in gray code. Okay, the important feature of this code is that there is only a single bit change between two adjacent codes. Okay, so because of this feature, it is also called as unit distance code. Okay, as only one bit changes at a time, the gray code is also called as unit distance code. Okay. Then with this introduction, we will convert binary code to gray code as well as gray code to binary code. Okay, so we will start with binary to gray code converter. Okay, so binary value is given. Okay, for that given binary value, we should find gray code value, right? So what is the procedure? So the MSB of gray code will be, okay, here the input is binary. Okay, binary value is the input. From that binary value, we are going to find the gray code. Okay, so the MSB of gray code will be exactly equal to the MSB of given binary number. Okay, then the next bit to MSB of gray code will be exclusive OR of the MSB and succeeding bit of the given binary number. Okay, that is, if both the bits are same, the result will be 0. Otherwise, result will be 1. Okay, that is XOR operation. We know the function of XOR gate, right? Both the bits are same, then result will be 0. Otherwise, result will be 1. Okay, so that is applied here. The other bit of the gray code will be equal to the exclusive OR of preceding and corresponding bit of the given binary number. Okay, so it should be followed until LSB. Okay, so here is the example how to convert binary to gray code, right? So here the given binary code is 11101. Okay, we need to convert this binary code to gray code. So what is the procedure? So here we are having 5 bits. Okay, so the MSB of this binary code is taken as MSB for gray code. Okay, so we are directly taking this MSB bit to MSB bit for gray code. Okay, so this is the given binary code, right? Then next bit, how to find the next bit? By XORing MSB and next bit position in the binary value. Okay, 1 XOR with 1. Bits are same, so result is 0. Again, this bit XOR with next bit. 1 XOR with 1. Again, result is 0. Then again, 1 XOR with 0. Okay, bits are different, result is 1. Because we are performing XOR operation, right? So again, 0 XOR with 1. Okay, that will give 1. Okay, so this is the gray code, right? So answer is 10011. Okay, so this is the circuit for binary to gray code converter. Okay, we know the Boolean expression. Okay, G3 should follow B3. Okay, G3 should follow B3. G2 is nothing but B2 bit position XOR with B3 bit position. Okay, like here in this example. Okay, B3. For example, here are 5 bits. B0, B1, B2, B3, B4. Okay, so here also gray code also 5 bit in length, right? So B4 should be G4, G3 will be B3, B4 XOR with B3, that will give G3, right? G2 is obtained by XORing with B3 and B2. Okay, G1, B2 XOR with B1, G0, B1 XOR with B0. Like that, here we are having Boolean expressions. Okay, so G2 gives B2 XOR with B3, G1 gives B1 XOR with B2, G0 gives XOR function with B0 and B1. Okay, so this is the corresponding logical circuit. Okay, so G3 is taken directly from B3, G2 is XOR of B3, B2, G1 XOR of B2 and B1, G0 XOR of B1 and B0. Okay, then another type, gray to binary code conversion. Okay, so here also we are going to follow a set of rules. Okay, so MSB of binary code will be, here the gray code is the input, binary is the output. Okay, so MSB of binary code will be exactly equal to MSB of the given gray code. Okay, then next bit to the MSB of the binary code will be exclusive OR of the MSB bit of the binary value that is obtained. Okay, and the corresponding bit of gray code, right? That is, if both the bits are same, that is XOR function, both the bits are same, result will be 0, otherwise result is 1. Okay, so this procedure is followed until LSB bit. Okay, so this is the example. So here is the gray code 10011. Okay, so this is the gray code given. So here we are finding the binary code. So MSB of binary code is directly taken from MSB of gray code. Okay, this one is followed here. Okay, directly taken. Then the next bit of binary code is obtained by performing XOR operation with MSB of binary and corresponding bit position in the gray code. Okay, so if you want to find for example, this is a 5-bit number, so here we will get B0, B1, B2, B3, B4. Okay, so this is where G4, G3, G2, G1, G0. Okay, so B4 is taken directly from G4. B3 is obtained by XORing MSB bit position B4 and G3. Okay, similarly B2. Okay, B3 XOR with G2. Right, then B1 that can be obtained by doing XOR operation with B2 and G1. Okay, then similarly B0. Okay, B0 can be obtained by performing XOR operation with B1 XOR with G0. Okay, so the result is 10001. Right, so to perform gray to binary or binary to gray, we should know the XOR function. Okay, then only you can follow this procedure. After following this procedure, you will get the correct result. Okay, so this is the logical circuit. Okay, so this is the Boolean expression for binary to gray code conversion. Sorry, a gray to binary code conversion. Okay. an XS3 code. So it is also non-weighted code, which is used to express the decimal numbers. Okay, for any BCD number, the XS code is obtained by adding just each digit with 3. Okay, so if you're having BCD number, from that BCD number, you can obtain XS3 code by just adding the value 3. Okay, with each bit position of the BCD number. Okay, so this is the example. If decimal number is given, then the decimal number should be converted into a BCD representation. Then that, along with that BCD representation, you can add value 3. Okay, so after getting BCD number from decimal value, we should add 3. Okay, 0, 0, 1, 1. Then you will get XS3. Okay. So alphanumeric codes. So next type of code is alphanumeric code. So alphanumeric codes are used to represent the several numbers, alphabets, and special characters. Okay. The following alphanumeric codes are very commonly used for the data representation. Okay. American Standard Code for Information Interchange, simply ASCII, ASCII. Okay. The second one is Unicode. So ASCII code having 7-bit representation. So due to 7 bits, you can represent 128 characters. Okay, that is 2 power 7. Okay, not 27, 2 power 7. Okay, so 2 power 7 gives 128 combinations. So you can represent 128 characters. Okay, but Unicode having 16 bits. Okay, it is a universal code. Okay, Unicode means universal code. Okay, this code having 16 bits. So because of this 16-bit length, you can represent large number of alphabets, numbers, and also special characters. Okay, so because of the 16-bit combination, it supports more than 100 languages. Okay, so you can create more number of combinations. Then the next type of code is error detection and correction code. That is, the one type of code is parity code. So what is meant by parity code? So parity code means it is additional code which is added to the message. Okay, to find the error available in the received data. That means it is mainly used for transmission purpose. Okay, at the sender side, we will generate the parity code and add with message signal, and then we will transmit the information through the channel. Okay, at the receiving end, the transmitted data will be received and checked for errors. Okay, so so at the receiving end, you can easily find out the errors. Okay, if there any error is available, you can easily find out the errors with the help of this kind of parity code. Okay, so here we are having two type of codes, parity codes: odd parity code, even parity code. Okay, that is simply represented as odd parity bit, even parity bit. Okay, so this is one example. If an odd parity bit is used for transmission, okay, I'm going to transmit some messages from sender side to receiver side. For that, I'm going to follow odd parity. Okay, so the information to be transmitted is 011010110. Okay, so this is the binary word which is to be transmitted to the receiver end. Okay, so for that, we should generate odd parity. Okay, so odd parity means the number of ones available in this message signal should be odd. The number of ones should be odd. So in the given information, the number of ones are even. Okay, so to make it odd one, we should add one more one at the MSB end. Okay, we should add one at the MSB end. Now, in this word, there are 5 number of ones. Okay, odd number of ones. Okay, so binary word with odd parity bit. Okay, so after adding the parity bit, The number of ones results in odd means that is odd parity. If it results in even, then even parity. Okay. So type of parity bit is decided by the sender. Okay. So this is the example for even parity. So this is the given message signal. So we need to transmit this message signal following even parity by adding even parity. So here we are having 4 number of ones, even number of ones. So there is no need to add 1, but we should add logic 0 at the MSB end. Okay, because the binary word with even parity should result even number of ones. Okay, so already in the message there are 4 number of ones, that is even number of ones. So there is no need to add logic 1. Instead you can add 0. Okay, so in this result we are having 4 number of ones, that is even number of ones. Okay, so this is the binary word with even parity bit. Okay, next we will move on to combination logic circuits. Okay, so what is meant by combination logic circuit? So this circuit having n number of input variables. So based on this n number of input variables, this circuit can generate m number of output variables. Okay, a digital circuit whose outputs depends only on the present combination of inputs. Okay, at any time, okay, the output generated from the combination circuit only depends on present inputs available with that particular combinational logic circuit. Okay, so it can have n number of input variables and it produces m number of output variables based on the combination of the logic gates designed inside the circuit. Okay. So example for combination circuits are, we know that adder, multiplexer, demultiplexer, encoder, decoder, magnitude, comparator, parity, generator, checker. Okay, all are combinational logic circuits. So how to design a combination circuits? Okay, if I'm giving the specification, so based on that specification, how to design a combination circuit? Okay, so for that we should follow some procedure. Okay, so from that specification, first we need to identify the number of inputs and outputs. Based on the given specification, first we need to identify the number of inputs and outputs. After that, we need to assign variables for each inputs and outputs. Okay, after that, we need to draw truth table. Based on the behavior given in the specification, we need to draw truth table. From the truth table, you can obtain the Boolean expression. After obtaining the Boolean expression, you can minimize that Boolean function to get simplified result. Okay, for that you can follow K-map or theorems. Okay, after that, after obtaining the simplified Boolean function, you can draw the logical circuit. Okay, so this is the example. So this is the given specification. The specification is, we need to design a combination circuit which has 3 inputs, 1 output. The output is equal to logic 1 when 2 or more inputs are equal to logic 1. Okay, this is the condition. Output is equal to logic 1 when 2 or more inputs are equal to logic 1. Okay, so based on that, we need to draw truth table. Okay, so before that, we need to find number of inputs and outputs. Okay, from that specification, you can observe that there are 3 inputs, 1 output. Okay, so you can obtain the number of input and output. Okay, number of inputs 3, number of outputs 1. What is next step? We need to assign variables to each input and outputs. Okay, so inputs are assigned with A, B, C. Output is assigned with Y. Okay, after that, we need to draw truth table. Okay, so for that, we need to understand the given specification. Okay, so output is equal to logic 1 when 2 or more inputs are logic 1. Okay, so here there are 3 inputs A, B, C. For that, we are having 8 combinations. Okay, in this 8 combinations. Okay, so we need to generate output as logic 1 when 2 or more inputs are logic 1, right? So you can observe that this combination having 2 number of ones, this combination also having 2 number of ones, this one having 2 number of ones, but this one having 3 number of ones. Okay, more than 2. Okay, for these 4 combination, the results should be 1. Okay, for other combinations, results should be 0 because the number of ones available in the other combinations are less than 2. Okay, so these 4 combinations having 2 or more number of ones. So for that we are generating output as logic 1. Okay, so from that truth table we need to draw Boolean expression. Okay, so here we are representing the Boolean expression in terms of sum of minterms. Okay, so this one, this one, this one, this one. Okay, so here 0, 1, 1 gives 3, 1, 0, 1. This is 5, 6, 7. Okay, I hope all are familiar with this procedure. Okay, how to get the minterm from this truth table, right? So based on that, you can get the minterms like this. After getting this minterm and formed the Boolean expression, we need to simplify that Boolean function. Okay, so for that you can go for K-map. Okay, so in this K-map, you can put the number of ones based on the minterms obtained in the Boolean expression, and then you can group. After grouping, you can get the minterms. Okay, after getting the minterms, you can sum all the minterms to get the simplified Boolean function. Okay, if it is possible, you can further simplify this expression like this. Okay, then you need to draw combinational circuit based on the obtained simplified Boolean expression. Okay, so this is the logical circuit. Okay, so clear? So the step 1 is we need to identify the number of inputs and outputs. Step 2, we have to assign the variables for each inputs and outputs. Okay, and then we need to draw the truth table. Okay, after drawing the truth table, we have to get Boolean function. Okay, this is step 4. In the step 5, we need to draw logical circuit using simplified Boolean functions. Okay. So next we will move on to arithmetic circuits. What is meant by arithmetic circuit? Okay, so the circuit can do arithmetical operations. Okay, what are the arithmetical operations? Addition, subtraction, multiplication, division. These are all arithmetical operations. If a logical circuit can perform these kind of arithmetic operation, that particular circuit is called as arithmetic circuits. Okay, so from that addition, from that arithmetic operations, you can find the type of circuits. Okay, the circuit which performs addition operation is called as adders. The circuit which performs subtraction called as subtractor. The circuit which can perform multiplication or division, okay, that are all called as multiplier, divider, respectively. Okay, so here we are going to discuss about adder circuit. Okay, so design of adder. Adder means addition operation, okay, which can be performed on binary data. A simple addition consists of the following 4 possible combinations of operation. Okay, you can add 0, 0, that will give 0, 0 plus 1 will give 1, 1 plus 0 will give 1, 1 plus 1 will give 1, 0. Okay, here 0 is sum, 1 is carry. Okay, similar to binary addition. So here we are having 2 types of adders. Okay, so that are half adder and full adder. Half adder means it is a 2-bit adder, 2 1-bit adder. Okay, it is a combination circuit that adds only 2 1-bit at a time. Okay, it can add 2 1-bit at a time, right? So it needs 2 1-bit binary inputs. Okay, that are named as AGN and ADDN. Okay, and produces 2 1-bit binary outputs. It generates 2 outputs, but both are 1 bit. Okay, so the outputs are named as sum and carry. Okay, if I'm adding input A, which is 1 bit in length, then input B, which is also 1 bit in length. By adding these 2 1-bit values A and B, a half adder can generate 2 possible outputs. Okay, both are 1 bit in length. Okay, sum and carry. These are the 2 outputs. And full adder. So full adder means it can add 3 1-bit values. Okay, at a time it can add 3 1-bit values. Half adder can add only 2 1-bit values, but full adder can add 3 1-bit values. Okay, for example, A, B, C. Okay, A, B, C, all are 1 bit in length. You can add A, B, C, 3 inputs with the help of full adder, and also this full adder produces sum and carry as the output. Okay, that are also 1 bit in length. Right? Okay, so now we will see how to design the full adder. Okay, so it is also applicable for design of half adder. So design of combinatorial logic circuit which add 3 bits at a time. That is full adder. Okay, so what is the procedure? We need to identify the number of inputs, outputs. Then we have to assign the variables with some alphabets. And then we have to draw the truth table. And then we have to get the minterms from the truth table. By combining these minterms, you can get the Boolean expression. After that, we need to simplify the Boolean expression using K-map. Okay, after simplified, you need to draw logic circuit. Okay, so first step is number of inputs and outputs. Okay, so here we are going to add 3 1-bit values. So number of inputs are 3. After performing addition, the circuit will generate 2 possible outputs, sum and carry. So number of outputs are 2. Okay, so you can assign the variables for input, output. So inputs are named as A, B, C. Outputs are named as carry, sum. Okay, CO represents carry, capital S represents sum. Okay, so based on that, you can draw the truth table. So here we are having 3 possible 3 inputs. For that, 8 possible combinations. Okay, so by adding these 3 bits, you will get sum and carry. Okay, so 0 plus 0 plus 0 will generate sum 0, carry 0. Similarly, 1 plus 0 plus 0 will generate a sum 1, carry 0. Here 1 plus 1 plus 1. Okay, 3 ones. If you are adding 3 ones, then you will get sum 1, carry 1. Okay, so all are familiar with this truth table, I hope. Okay, so after performing this truth table, we need to get Boolean expression for each outputs. Okay, we need to get Boolean expression for sum as well as carry. Sir?
Salutkumar sir, the time almost 12:46 ஆயிடுச்சு. இது full order ஸ்டாப் பண்ணிக்கலாம்.
Okay, so for each outputs we need to find the minterms. Okay, so here I'm going to find the minterm for sum output. Okay, so how to get the sum minterms from the sum output? We need to identify number of ones available in the sum column. Okay, here is the one, here, here, here. So for there are 4 ones. Okay, so the corresponding input combination is 0, 0, 1. 0, 0, 1 means 1, the minterm 1. 0, 0, 1, the minterm 0, 0, 1 can be represented as 1. Similarly, here 2, here 4. This can be 7. So there are 4 minterms that are 1, 2, 4, 7. Okay, 1, 2, 4, 7. Okay, that is belongs to sum output. Similarly, for carry output, here you are having 4 number of ones. Okay, this one belongs to 0, 1, 1. That means 3. Okay, here 1, that represents 5. Here, 6 and 7. Okay, so 3, 5, 6, 7. So these are the sum output, sum of minterms for carry output. Okay, so based on these 2 outputs, you can draw the K-map for each output. Then you can simplify the each output Boolean expression. Okay, so after performing simplification using K-map, you will get the result like this. Okay, sum is equal to A XOR B XOR with a C. Okay, or you can represent like this: A prime B C prime plus A prime B prime C plus A B C plus A B prime C prime Okay, for carry output, AB plus AC plus BC. Okay, so based on this Boolean expression, you can draw the Boolean circuit or logic circuit. Okay, so this circuit represents full adder. Okay, so you can also follow alternative method, right? That means here in this circuit, we are design the full adder using basic gates alone. Okay, it is also possible to construct the full adder using half adders. Okay, by using two half adders, you can also design one full adder. Okay, for that you can follow this alternative method. Okay, so these minterms are expanded like this. Okay, then you can simplify like this. After simplification, you will get the Boolean expression for sum. A XOR B XOR C. Right? Then for carry, here also, using Boolean theorems, you can simplify the expression, then you will get a Boolean function for carry output. Okay, based on these two functions, okay, this one AB plus C dot A XOR B and this one A XOR B XOR C. So based on these two expression, you can draw the logical circuit for full adder like this. Okay, so here this circuit, okay, HA represent half adder 1, HA2 represent second half adder. Okay, with the help of these two half adders, you can obtain some output A XOR B XOR C. Similarly, the carry output AB plus C dot A XOR B. So like that, you can design any kind of combination circuit following this kind of procedure. Okay, so we need to identify the number of input output. Then second step, we have to assign the variables for each input output. Then third step, we have to draw the truth table. Fourth one, we have to get the Boolean expression from the truth table. Fifth one, in fourth step, you have to simplify the obtained Boolean expression. Okay, then fifth step, you have to draw the logical circuit. Okay, so similarly, you can also design a full subtractors. Okay, so with this, we will end this session.